Hello. So in this lecture, we are going to look at the role played by refractive index of the gain medium. Until now, we have not paid much attention to the refractive index of the gain media, but as you can clearly see, we are within the gain curve, we are reasonably within the highly dispersive region of the refractive index. For example, if I talk about the absorption, which is just the negative of the gain, uh, in the case of absorption, we would be well within the anomalous dispersive region, right? So it is this dispersion which is varying, and let's see what is the consequence of such a large variation of the dispersion on the cavity frequency that is supported by the laser. So let us begin with a bare cavity. So you know that if L is the length of my cavity, then if I fit in lambda by 2 times integer, these are the modes that will be supported by the bare cavity. So I'm calling uh, this bare cavity modes. So you see, I can write down my frequency as m times c by 2l, right? And this is what I would define as nu m, or this is what is called these are the bare cavity modes. That is, I have a empty cavity without any active medium, and these are the frequencies which are supported. Now, recall that in our laser cavity, what we had was this the cavity mirrors. We had a finite length of the gain medium. So this was indicated as small l in our earlier notation. We'll stick to that. And this, the cavity length is capital L. Right. So you see that I can write down my capital L as small l plus L minus small l. So you see that small l is the length occupied by the gain medium, whereas capital L minus small l, this is the length which is occupied outside the gain medium. So you see that clearly if I'm looking at optical length, then you see that my optical length L in this situation is simply n of nu, which is the refractive index which is can be associated with the gain medium, for example, right? N of nu times small l plus capital L minus L, right? So this becomes my optical length. So let us put this new length, the optical length, into my older equation. So I have my bare cavity. So nu is mc by 2. The L I am opening up as the optical length, which is n of nu. There is small l plus capital L minus L. So I take mc by 2l common on the top, and you see that I can rewrite this in the following fashion. This becomes 1 plus n of nu minus 1 small l by capital L. Now this is what is my new frequency. If I rearrange this, I get the following form. And what I will do is I will identify my MC by 2L as simply nu M, right, which is the bare cavity frequency. So what I get is the following form. I have nu plus, I'm taking this on the top, which is n of nu minus 1 times small l by capital L multiplied by nu equals to, on the right hand side, all that I have is the bare cavity frequency, which if I rearrange can be written down in the following fashion. Nu m minus nu equals small l by capital L n of nu minus 1 times nu, right? Now you would recall that we have already seen the anomalous dispersion, uh, well, that is associated with the refractive index when we are within the region of resonance. So let me quickly recall for you the refractive index as we had written down earlier. So this, I'm just writing down the real part you are familiar with. So I can write down my n real. This is coming from our older discussion on the refractive index. Let's say my background refractive index is 1. So what I'm going to do now is rewrite this in a form that you are also familiar with, which is my n real minus 1 can be written down as lambda naught by 4 pi. And now I'm converting omegas to news, which is factors of 2 pi divided by delta nu naught and a of nu. My betas are related to delta nu naught. So with this expression, you can see that around the resonance, right, our dn over d omega is negative, right? So this is what is, we are well within the anomalous region. That is our region of interest. The other important thing I want you to realize is that my g of nu is simply the negative of a of nu. You recall how that happened? Remember, my g of nu was sigma nu times n2 minus n1. When we have n1 is all the atoms, the number density of atoms in the excited state is 0. That would mean that this is when I identify sigma nu times minus n. This quantity is precisely uh, what we call as a of nu, right? So that is what I have captured here. And because we are in the near resonant region, we want to stick to this definition. All right, so let us put this back into our expression. That is our equation number 1 that we have. So what I get is nu m minus nu equals nu times small l by capital L times this expression of n of nu minus 1, which is minus lambda, let's say 2 1, which is the resonant frequency associated with the atomic resonance or the active medium. Then you have nu 2 1 minus nu by delta nu 2 1 times g of nu. We will quickly recognize that nu is quite close to c by lambda 2 1, right? Nu 2 1 is exactly that, which is quite close to. All right, so I can rearrange this in the following form. I can write my nu as nu 2 1 times this particular factor, which I will identify as the cavity line width, but let's just first write it down. Small l divided by 4 pi capital L plus nu m times delta nu 2 1 divided by c g of nu small l by 4 pi L plus delta nu 2 1. I have simply rearranged the above equation and obtained this. Now I identify that this quantity in the bracket, right, C times G of nu small l by 4 pi capital L. I identify this quantity as delta nu C, or as the cavity bandwidth. This is a definition which I will justify in just after this discussion is over. So I can essentially write down, this is my final equation. I can write down nu as nu21 times delta nu C plus nu m times delta nu21 divided by delta nu C plus delta nu21. Let us remind ourselves of these uh, individual quantities. Remember, nu21 is the resonant frequency associated with the active medium. Delta nu C is the cavity bandwidth, right? Delta nu21 is the atomic or the active medium's bandwidth. Nu m is the bare cavity frequency, and you have the two bandwidths at the bottom. So you see that the frequency at which the laser oscillates has got to do with the bare cavity frequency. It is not really that. It is not really the resonant frequency of the atomic system. It is actually a compromise between the two. And this I'm calling it as equation 2. Let me rewrite this. So this comes out to be delta nu C times nu minus nu21 equals to delta nu21 nu m minus. So this is a very interesting equation. Let me call that equation 3 because of the following reason. Nu is the frequency supported by this is the laser frequency that is actually oscillating. Imagine that my laser frequency was smaller than one of the modal frequencies, which are the bare cavity frequencies. In that situation, this my right hand side of this equation would be positive, right? Because nu is smaller than nu m. Clearly, that would mean that for the left hand side to be positive, nu has to be larger than nu21. That is, there is a competition between atomic frequency and the bare cavity frequency. And the actual laser frequency, which actually oscillates, is actually being pulled on either side by the resonant frequency of the atom and the bare cavity frequency of the cavity. Let's look at it a little pictorially to make sure that we understand where we are. Imagine this is my frequency space. This nu21 is my atomic central frequency, and I have got this series of frequencies which are equispaced. So this is nu m, and what you have is that the lasing frequency has to essentially operate in such a manner it is being pulled by the atomic frequency on one side and by the bare cavity frequency on the other side. It has to reside somewhere in between. So you see, this is what is the notion of frequency pulling. We no longer have a bare cavity where the frequencies are simply determined by the length of the cavity. We also have another resonant frequency, which is that of the atomic system itself, the active medium. It is trying to pull the frequency towards itself. It's an interplay between these two effects that leads to the eventual oscillation of a particular laser frequency. Typically, you would see that our delta nu 21, which is the homogeneous line width associated with the atomic system, is much larger than the delta nu c, which is associated with the cavity bandwidth of the cavity. You typically have a very large lifetime of the cavity, hence a a very narrow bandwidth for the cavity. So in this situation, I can uh, put this quantity into 3 and then look at a Taylor series expansion of nu. So my nu can be written as almost equal to nu m plus nu21 minus nu m times delta nu c by delta nu21. Remember that this is a small quantity, so I am limiting myself to only the first order. So what you basically get is the following. So imagine that there are multiple longitudinal modes within the cavity. So imagine that my new, now I'm, this the bracket ones are the lasing frequencies. So I'm looking at m plus 1 minus nu m. This is now the spacing between the various multiple modes of the lasing frequencies. You see that this particular difference in frequency is now simply the following. It is nu m plus 1 minus nu times delta nu to 1 divided by delta nu c plus delta nu to 1. See, right? So clearly you would see that the original difference, so this was the original difference between the bare atomic frequencies. It is no longer so, and what you get is uh, remember that nu m plus 1 minus nu m is simply c by 2l. So you see what you get is that the difference in frequency is no longer the bare cavity difference, but it becomes smaller by this factor, which is 1 over 1 plus delta nu c by delta nu to 1. See, right, this is the now the frequency spacing. So what has happened is that the frequencies have been pulled, or the mode spacing from c by 12 has been reduced to this new quantity. So this is the effect of frequency pulling, and clearly the frequency pulling effect is larger as delta nu c becomes larger and larger. So let us see what is delta nu c. As I promised, I will justify what is the cavity bandwidth, and let us look at that cavity bandwidth. And why did we call that combination of terms as the cavity bandwidth? Now remember that the equation governing the intensity within the cavity, di nu by dt, was simply minus c by 2l 1 minus r1 r2 times I nu. This would be the loss of intensity to the cavity coming out of the finite transmission at the mirrors, right? And I'm not now considering the active medium because I want to look at the bare cavity and its bandwidth. You'll also quickly recognize that this can be written in terms of the threshold gain condition, right? So I can write this as C times small l by capital L, and identify that C by 2 small l 1 minus r1 r2 is my G threshold, right? And this times I knew. So this is precisely is the rate equation that governs the intensity inside a bare cavity. For such a rate equation governing the intensity, I can write down intensity as a function of time quickly. I knew at time t is I knew at time t equal to 0 times exponential minus c small l by capital L G threshold times t. Clearly, you will see that my intensity is decaying in time. For such a intensity, I can essentially guess what the electric field of the electromagnetic wave whose intensity is decaying will look like. So I can write down my E nu of t as simply some E naught at time t equal to 0. The amplitude itself decays by half of this, which is C small l by capital 2L now times G threshold times T. And of course, the electromagnetic wave has got a central frequency, which I am writing as exponential minus 2 pi I nu times t, right? Exponential minus I omega t. This is my electric field that describes the electromagnetic wave that is decaying out of the cavity with this intensity dependence. Clearly, I can write down the spectrum of this. So you know that if I take a Fourier transform of this, I would get a spectrum which is Lorentzian because the exponential decay results in Lorentzian. And you see that the corresponding spectrum which I would get is going to be of this form. So my S nu prime, which is the spectrum associated with the light here, it is going to be simply delta nu C by pi nu prime minus nu the whole square plus delta nu C whole square. Remember, nu is the fixed frequency uh, of the oscillation, and this is the spectrum about it because we are looking at its width. And you see that delta nu C is precisely what we had identified earlier. When you do the Fourier transform of this above equation, you see that my delta nu C is indeed 1 over 2 pi C small l G threshold by capital 2L, and this is what we call as the cavity bandwidth, right? Um, by the way, there is another quantity. If you recall, we had discussed something called the quality factor associated with the cavity. That is simply defined as 1 over 2 nu by delta nu C, right? Smaller the value of the bandwidth, that's narrower the spectrum, better is going to be the quality factor. So we see that the larger the cavity bandwidth, greater is the effect of frequency pulling in this system. So we figured out two conditions that for large effect of frequency pulling, right? Frequency pulling is being different from the bare frequency separation. So large frequency pulling happens because of two things. One is for high values of the G threshold, like larger is the decay, and also for narrow gain profiles, right? That is delta nu 21 is small and delta nu C is large. Correct. So this is what leads to this business of frequency pulling. Now these discussions for homogeneous broadening. So a small caveat. We have undertaken this calculation for homogeneously broadened active medium delta nu to 1, but let us say we have a inhomogeneously broadened line shape. In that case, delta nu to 1 will be replaced by the inhomogeneous broadening line width that you get. So this frequency pulling effect is it indeed happens in all lasers, and the frequency of oscillation is always going to be pulled away from the bare cavity frequencies towards the central frequency of the active medium. So with that, we bring this lecture to a close. And in the next lecture, I will talk about this competition between single mode and multi-mode nature of lasers and what is the role of the broadening mechanisms in obtaining that.